Okay, perfect. Thank you for everyone. I am the CEO of Optimal Energy. Optimal Energy is a Brazilian startup. You have been founded after some years of experience I had in the energy sector, and now you have some financial support of investment funding. I am the CEO at Optimal Energy, but I have a long history in both subjects, also in machine learning and in the energy sector. I have made my postdoc in artificial intelligence at the Imperial College in London in 2006, so 2007. I have also a postdoc in objective optimization from a Brazilian university called Federal University of Minas Gerais. I hold my PhD in machine learning from Oxford University in UK and also from Federal University of Minas Gerais. And it's been about 12 years of experience in the energy sector. And during this time, always using the technologies I'm going to talk about. Of course, some of them have developed deeper than others. And in this presentation, I'm just going to highlight some of the ideas you have been through in the past years. And I still a researcher, not only in the practical aspect, but also I'm doing some scientific papers, so trying to understand better the solutions, what we can do, and how things can work. In this presentation, we have some clients, but I'll have the focus on two of our main clients. That's CEMIG, that's one of the Brazilian energy providers, and Norte Energy. Norte Energy operates Belo Monte, that's the third biggest hydropower plant in the world, and it's smaller than Itaipu. Itaipu is bigger, but it's a very important power plant. It's a newer one, so there we are still learning how to operate. It's a very complex operation. It's a complex operation for a simple reason. It's on the north of Brazil, on the Amazon forest. It's a very flat region, so it's very different from the other power plants we have, most of them. And since it's very flat, very small difference in the height can make loads of difference in the energy that's generated. So the efficiency it changes a lot if small difference. So all the cases I'll talk here, there are real world cases. Some of them I cannot provide the full data, so I'm just gonna show some highlights, and some of them will provide a deeper insights of the data. But first, I'd like us to talk a little bit. I know that most of people here, like me, I am an electrical engineer, and they are more connected to the hydropower problem than to the machine learning community. And I just draw here some of the terms that you may listen. They are closely related. They are not precisely the same thing, but they help us to solve similar problems. Artificial intelligence is a broader area of intelligence, if I may say like that. Machine learning is what is more practical, I could say, because machine learning is about doing artificial intelligence in machines. The artificial intelligence can be made in any device, such as biological device, for instance. But machine learning is a term that I like a lot. Probably some of you have already listened about deep learning. Deep learning is a subclass of neural networks. That's a class of machine learning. Deep learning is when you have loads of data and you can make complex neural networks to work. It's very common in internet-based applications because there are plenty of data. For instance, like Instagram. When I started my PhD in 2003, I used to work with computer vision that's extracting information for images. And that time, it was the beginning of the digital cameras and those devices. You don't have strong social networks. And I would go to the internet. I was trying to make a detection of cats. So I could go there and I have 3, 4, 5 photos of digital photos of a cat. And I used to make some techniques to rotate and zoom in, zoom out this photo. So I could get with a database of 100 up to 200 photos. If you go today in the Instagram right now, and if you go hashtag Instacat, probably you're gonna find over 30 million photos. So probably every single cat, domestic single cat, has a photo on Instagram. So it has enabled us to use different techniques that among them are deep learning. And then you talk about having loads of data, it's what you call big data. So in two aspects, we have in many cases big data, but in the electrical power sector, you also can understand big data when you have real-time data. So it's another thing. Data science is looking right from the beginning of the data and also data analytics. So I'll talk about some of the applications you have. So when you talk about flows in general, so the companies, they are looking for weather forecasting if the support of machine learning, and it can increase your precision using the traditional techniques together with the machine learning. The other things you can have is the natural inflow forecast. You have to connect both weather forecast with the natural inflow forecast because they're not exactly the same. As you can see in this figure, if it's raining in one, you have to understand how much water you get to your power plants. But I will highlight here one aspect that's a little different from what most of people are looking for. It's the delay time, the water delay time between plants. Most of the companies we have worked with, all of the companies we have worked with so far, we have a fixed delay time. So say it takes 16 hours, 18 hours, 4 hours, or 3 days for the water to get to the upstream plant, to the downstream plants. But indeed, when you look to the data, you find out it's not like that. It's non-linear. It depends of the flow itself. So if you have a higher flow, usually you have more velocity. It depends of the season, especially on the power plants up to the north of Brazil, because if the dry season, the river is complete, it behaves completely different than from the wet season. So it depends on many other factors. And curiously, if I look to short-term operation, if you have a runoff river power plant that's downstream to a power plant reservoir, the operation of the upstream power plants makes a huge difference in the operation of the downstream power plants. In most of cases of our studies, it's more important to predict or to use properly the operation of the upstream power plants than to predict the weather itself. Because if you are looking for a huge reservoir on the upstream power plants, it has much more water than your uncertainty in the weather forecasting. So this is one application we have made so far. So in case of one power plant you are working with, you need to have the delay time for each month and depending on the flow, because it changes a lot if the season. The same thing is about the water losses. So if I'm modeling the water losses, it depends on several things, and most of the models, they consider it linear, and it's not linear. In here, I'm just providing an example. It's real data. Is the relation of the natural inflow and the height variation in a power plant. And you can see in the red line is the traditional polynomial modeling, and it clearly doesn't work. And since it's the real data, you have, of course, future outliers, took out some noises and those kinds of things. So you can see you need a more complex model for decreasing the error. So you have to include the other variables on the model. So in here, you have a huge error in some moments. So when you include the other variables, you cannot visualize because it's not 2D or 3D, but you get a much smaller error in your prediction. I'm telling about prediction because part of the work that people are interested in is, okay, what I do in the next hours, in the next days, in the next months, or on our power plant. So in the X, you have the natural flow, and the Y-X, you have the height variation. So it's clearly very nonlinear. Here I'm going to provide another example that's interesting. It's how to tell the history of data. The Tommaso presentation was very nice in this sense as well, because it has provided many nice graphics to present. And here is the data storytelling. It's one power plant, and you try to understand if this is a heat map. How does it evaluate its generation compared with the planned generation? So you can see it changed a little bit during the weekdays, the weekends. It operates closer to the planets, but during the week, and especially in the main hours of the day, it doesn't operate tight to the planet. What happens in this case is because in Brazil, you have a central operator that just take the phone and send a message. Okay, I need more energy now. Now it's fine. I can have less energy. So this is another aspect that's very interesting in the use of machine learning techniques in the hydropower context. So you have many different ways of telling the data history. So you have the technique that you call data storytelling. So heat map is one of these, one very simple technique of doing that. Outlier detection. In here, I took a very extreme example, but you have also machine learning techniques that can keep all the time looking for your incoming data. So it's very important when you are looking for in real-time applications. And if the data behaves like an outlier, it can provide an alarm. An outlier is not precisely based on bounds. So if you can make this, of course, it have been discussed previously, using bounds to be outliers, but it's much more complex than that. In this case, for instance, it's a parallel power plant. So they have two power plants. So the discharge of one power plant depends on the other power plants. It depends on the historical data. It depends on the upstream and downstream heights and everything. So another application that is very interesting and it's necessary for real-time optimization is outlier detection. Is another way to use machine learning in this context. So now I'll go a little bit about digital twin, and I'll finish it showing some cases that apply both together. So what is digital twin and what is the cyber physical space? Those terms, they are studied and considering under the Industry 4.0 context. Basically, it's how you connect your physical system with your digital system. So your digital system, it's a copy as accurate as you can do. Of course, you have always to look what question are you trying to answer to not make it overly complex. And this connection between the digital and the physical provides lots of information of what you can do. So you get data from the physical, you run in the digital, you provide decisions on the digital space. So you can come here and say, if I do this or that, what is the impact? Take this decision, provide the decision to the physical space, having the feedback from the physical space, and so on and so forth. Nowadays, you have 18 power plants with a very detailed digital twin that has the focus of operation planning. It's different if you have a digital twin for maintenance, for instance. Our focus in the moment is planning. So what are the components of a hydropower digital twin like the one you have right now? So of course, you need all the data of your power plants. So you have to understand what is the loads curve that you have to the future. You are measuring the reservoir heights and also may have a target. So this is what you are looking for the operation in the future. You have some water availability that includes weather forecasting, water delay time between power plants, among others, the natural inflow. You have the reservoirs heights, and also you have the modeling height to volume to us to understand. So you have to make a hydric balance. Of course, you have the generating units and also the hill curves. So as precisely you have the hill curves, more things you can make. You have some operational rules, like you want to maximize your efficiency, you have to meet your load curves. So for doing that, you need to look to unit commitments for the turbines. You have to look for many constraints. When I say many constraints, it's electrical, mechanical, environmental constraints, and also regulation constraints. You make the water level balance, and this all has to be made together in a very fast fashion. This is the main idea of some components of the digital twin of hydropower plants, considering planning aspects. Here is a real world example. Most of the text is in Portuguese, but in here, just for you to see, it's the Belo Monte power plant. So during the day, you have about 0.43 deviation from the planning to the real that was made on the power plant. So you can see, if you have a nice digital twin, you can be very accurate between what you have planned and what you are executing in the real time. And it is very nice because if you go to more freely regulated markets, your decision becomes when and how should I generate energy, because the price changing through time. So you have to make, okay, I want to generate in this way or in this other way. Your decision starts to be more relevant and more complex. Another point that's very interesting when you put together machine learning, digital twin, is that you can have a more precise ESG in your company and your power plants. ESG is about environmental, social, and corporate governance. So when you say that, it's very hard for you to get to the corporate governance if you cannot have proper data that you can audit and it's accountable. So for doing that, what you are providing now is tools that you can collect the data, make the calculation, and provide the insights. So here on the right side, you have a graphic of some violations that one of the power plants that you are operating have made in 1 month. So in this case, some serious one, like environmental discharge, was violated by many times during the month. So when you do that, you have to put together your physical model that has to be the environmental constraints. When I say environmental constraints, it's about how much discharge you have to make in an hour or in a day, what is the allowed discharge variation, all those kind of things. So we call the environmental constraints. Of course, you have the physical constraints, that is the forbidden zones, forbidden operating zones. So you need to see how the extent of the operation zones, the unit commitments of the generation units, among others, electrical constraints, regulatory constraints. So everything must be taken into account. So this, since you are looking now, that's very serious, the ESG aspect in every company, this type of questions are very interesting and necessary, and digital tools are coming to help solving and providing more accountability on those aspects. And here I'll present a little bit also about optimization. So after you have a proper model, you can start optimizing your power plants. So here is a Brazilian power plant. It's called Três Marias, Three Marlinas. And this is a very old Brazilian traditional, not old, traditional power plant. So in here you have 2 ways of optimizing. It's a previous method you have developed in our company. This one is one state of the art that you can see in scientific paper, and this one is the way the official Brazilian programs they run. So in our case, if you see, yeah, and when they are compared, if the generation optimized, you can see you have saved about 40,000 hectometer meters in 1 month. So it's a small power plant. It was just about planning. It didn't change any income. It didn't change the inflow. Nothing of that. Use this, but planning how you tune on, tune off, look in the maintenance, the viability, the efficiency of the turbines. Just doing this calculation as best and as fast as you can, you could get about 46,000 hectometer meters. And if you look at this in Brazil, it's not precise like this, the market, but if you look at this, the energy in the market price should be about 2.2 million reais, just 1 month of extra energy. So I have 1 more minute. I'll try to show you just a little bit of the system running live, just for you to have an idea of what it can take place. I hope you can see the system now. It has just updated. It's in Portuguese, sorry, it's in Portuguese. But here is a cascade. So you have 3 power plants, 4 power plants. 1 power plant in the middle is from another company. So you don't have the data fully integrated between the plants. You can see here the availability of the turbines. So if they are in green, they are available. So they can be in synchronous and also can be not available if they are in red. So you collect. Here is generation, real-time generation, and in the right side X, and in the left side is the height. So it's the height of the power plant. So you can follow everything in real time. Here are the outflow of the power plant. So you have all the data here in real time. If you look here, let me, in this case, in Brazil now is 10:30 in the morning. So up to here, you have the real data collected for the generation. And from here on, you have the planned generation for this power plant to follow some constraints and some regulations. So this is an online cloud solution that you have provide, and it's working now in 15 power plants. So that is it. Thank you very much. I'll provide my contacts in the next slides.